Hi, my name is Frazer, and this year I've been looking into computer vision for yarding operations and specifically evaluating single-stage instance segmentation for grapple carriage yarding for Forestry 410. I'm going to get into a little bit more about what that means in just a second. So a bit of background on why I chose this project. As all people in forestry will know, we're innovators. We're always looking for a way to improve productivity, decrease our costs, and get better outcomes for our workers. And for me, I decided that automating our machinery is one way to achieve this. Yarding of logs in particular, it's a relatively repetitive task. It's by no means simple, but it has a workflow that could benefit from a partial or full automation of parts of the job. And as an aside from being good for productivity, this may really help to improve the working conditions, reduce mental load on our workers, and attract more people to the industry. Now, a bit of an overview about machine learning, which is the tool that I've applied to this problem. It's a branch of artificial intelligence where the basic premise is that you're teaching a computer to learn based on examples of what something is. And in this case, it's teaching the computer what a log is in the cutover environment. Machine learning and artificial intelligence have made huge gains in the last few years, especially as computing power has really increased, and also access to open source software to apply to these domains. This means everyone can get stuck in and have a go at using these techniques on their own applications, and we've seen mining and farming take these up in similar domains. One particular application of machine learning is instance segmentation, and this is identifying the exact outline of an object in an image and recognizing that multiple of these objects may be present in each image. And this is important because of the environment that we're in. Now, the algorithm in particular I've used is known as YOLACT, and again, it's a single-stage instance segmentation algorithm, and in particular, it's designed for real-time application, so it works really fast at identifying those objects in the image. You can see from that diagram that it recognizes that each of those separate objects is an elephant and picks out their exact outline, which is what we want to do with logs. So yeah, the study objectives primarily evaluate the accuracy of the real-time YOLACT software in this domain. This is important because if you're going to use it for automation, you do need to pick out the logs. Secondly, we want to evaluate the speed when inferencing on a video to determine if it's going to be appropriate to put in a machine and process fast enough. I want to generate some labeled data sets, so if someone else decides to continue work in this domain, they have a starting point to go from. And I also want to compare between different video resolutions to determine what effect that would have on performance and speed as well. So I collected two data sets. The first was from DC Equipment, and they were nice enough to help me sort out a recording operation on one of their grapple cameras, and we collected about 10 hours of footage from here. Now, the DC grapple camera footage does come in slightly higher quality than what I got, but because of the compression of the video camera, we were at a resolution of 720 by 408p. The second data set was from a yarding operation in North Canterbury. We took this with a drone, which got really high quality footage. Only about 15 minutes of it because of the way that we were able to fly over a lot of logs in that 15 minutes. We were able to get a lot of target logs to use for the data set. Split these footages at 2-second intervals, which generated thousands of stills of DC and about 170 for RANAir. Now, from these images, I had to select what I wanted to have for my final data set. The main criteria was that there was minimal blur. Obviously, camera in motion has blur sometimes, but I tried to take images that were clear. I wanted the log to be well lit, so in the sun with sort of clear lighting on it. But I did decide it was okay if the log was partially obscured. So in the forestry environment, it's typically pretty messy. Probably not going to get all of our logs well presented with no slash or other logs on top of them. So I decided that this would be an acceptable criteria for the logs we were looking to grapple. In the end, I took about 114 images from the DC imagery and 32 from the RANAir. And I labeled them or masked them using the Label Studio tool, which you can see an example of in the slide there. And then I trained the model. So in this step, the data that I've annotated is split up into a training and a testing set. The training set is provided to the model first, where it sort of gets an understanding of what a log is. It then tests these assumptions on other annotated images where it makes a guess at whether the mask is going to be in this image, corrects its original parameters, and through a process of iteration learns what a log is. I use what's known as transfer learning through the ResNet 50 pre-trained model. This reduces the data requirement for training the model to a good level of accuracy. It just provides some context for the model of what physical objects in the real world are. Train it for 2,000 epochs, which is just full passes of the data, but it actually reached a sort of steady state of accuracy before this. And measure the performance with average precision and an IOU threshold of 0.5. Now, just quickly on that, average precision is a measure of accuracy that takes into account both false positives and false negatives, which is important for a detection application. And then it's set an IOU threshold. So previous studies have indicated that 0.5 was going to be an appropriate threshold for this, and you can see an example there of what 0.5 looks like. So that's what I chose for my evaluation as well. And so the results. We were able to train the model to recognize logs. Unfortunately, the accuracy didn't get to where I would have hoped or that would be appropriate for an actual application. The speeds, however, were really good. Managed 50 frames per second on the DC data and 31 on the Ryanair, which exceeded my expectations. And did create those two data sets with about 200 masked logs in each one. So you can see highlighted in this table, the mask AP achieved for the DC data, which is the accuracy, was about 13%, but really did hit high 50 frames per second. And the mask AP for that Ryanair data was 21.6%, and again, about 31 frames per second. So yeah, in conclusion, really good speed performance, but poor predictive accuracy was the main takeaway. However, achieving better performance was correlated with higher resolution data. There's a lot of reasons why I think this might have happened. In general, machine learning algorithms are a bit of a black box. It's hard to understand exactly why the machine did what it did. But in my opinion, I think the difficult environment makes things an issue. A log is actually quite similar to its surroundings. So discerning between what's a log and what is just a branch or other sort of woody debris beside the log or slash is actually quite difficult in this application. In addition to this, the logs appear in a really wide variety of poses and sometimes do have quite different features. So some logs will have stripped bark, some will have a butt present, and all these things make it hard to get a consistent object for the machine learning model to pick out. Again, the data set wasn't as big as it could be and certainly not as large as it is for some machine learning applications, but this was just a limitation of the study timeline. In summation, I believe that YOLACT itself is probably unlikely to provide the accuracy needed for a commercial model, but that these techniques, machine learning, another combo, another algorithm, or perhaps a detection algorithm with a pose estimator over top may provide the accuracy we need in the future. For anyone looking to work on this task in the future, my main recommendations would really be to make sure you have really high quality footage or imagery, explore a range of different methods in open source software, and try to get a really accurate mask on what you're looking for. Cheers.